Welcome everyone to this video. Um, so we are going to discuss today pressure exerted by a fluid at a depth h. So basically our lecture is going to contain some theory and some questions and mostly questions only because that is the best way to understand a certain topic. So let's begin. So what we are learning today is pressure by a fluid at depth h. So what do we mean by that? Basically, we say that okay, if there is a fluid contained in some kind of container, let's say that container is drawn like this, it has some fluid drawn up till some capital H height. So up till H height, we have filled this fluid whose density is rho. Density is something which we studied yesterday in the previous video, and it is defined as mass per unit volume of fluid. It helps us in defining whether the fluid will stay on top of the fluid or whether it will stay at the bottom. So it's pretty important that we have the density of the fluid because it tells us the amount of pressure it's going to exert. So naturally we can feel if its density is more, the pressure is going to be more. Similarly, if we have more acceleration to gravity g, then also the pressure is going to be more. For example, if let's say we have water contained in a bottle and what pressure it is exerting at the bottom of the bottle. And now we take that bottle to moon where G is different. Where by G I mean acceleration due to gravity. At the surface of moon, the value of G is 1 by 6 times that of Earth. So because of that, the pressure exerted by the particles at the bottom or at any h depth beneath the surface is going to be less. Okay. Now we are going to also take a point H, point P at a depth small h, right? So now we have to basically find what is the depth at the P point, right? So as such, the depth, the pressure at point P is simply guided by the atmospheric pressure. The atmospheric pressure is represented by P naught. This is atmospheric pressure. So what its value? For value, we say its value is some 10 to the power 5 times 1.015 Pascal. So this is the total pressure exerted by atmosphere uh, on the sea level at all particles. So this pressure basically gets added up to any pressure we calculate inside a fluid. So whatever pressure is exerted by this part of the fluid, that is this particular part at point P, we will add this atmospheric pressure as well. So this then becomes the total pressure at point P. So what is the pressure exerted by this part that we have to find? So that value is simply represented by delta P. It is called gauge pressure. So the value of gauge pressure, that is delta P, if we add that to P naught, we'll get the total pressure at depth P, with whose value P is equal to P naught plus delta P. So there is a net pressure at point P. Net pressure or absolute pressure. Now I also want to discuss what are the different units which we use to define the uh, which we use to represent the atmospheric pressure at a particular point. So Pascal is one of the units, but there are other units as well, which we should take note of. Yesterday we discussed simply Pascal, that what Pascal is by the definition of force or by the definition of pressure. So pressure, one Pascal is equal to 1 Newton per meter square. That is, if a surface which is 1 meter square in area is acted upon by a force whose magnitude is 1 Newton, then the pressure on the surface is 1 Pascal. So we have one more unit which is equal to 10 to the power 5 pascals. It is 1 bar. So 1 bar is 10 to the power 5, 10 to the power 5 pascals. Then we have uh, 1 centimeter of mercury. So this is what is basically related to a particular depth of a fluid. That is 1 centimeter depth of mercury represents this much pressure. So this is 1 centimeter of mercury, and this is also a unit of pressure. We say 76 centimeter of mercury is equal to 1 atmosphere. So 1 atmosphere is the pressure exerted by the surrounding air on us. So using that, we define what is 1 centimeter of Hg. So 76 centimeter of mercury is equal to 1 atmosphere, which is written as 1 atm. So atm is short for atmosphere. So this is the normal pressure which is around us, I hope. So this is 1 atmosphere, this is 76 centimeter of mercury. Then 1 centimeter of mercury is also equal to 1 torr. This is also a unit of pressure which we may encounter sometimes. But the SI unit of pressure is 1 Pascal only. This is the SI unit. So moving on. So what about the pressure delta P? That is the pressure exerted by that particular section of the fluid at a depth h. That is, if I have selected a section like this inside the fluid of density rho, there is atmosphere P naught above is, then what is the pressure at the bottommost point of this selected volume? So to find that, we will say what is the weight of this particular volume. We have to figure that out. So to find the weight of this particular volume, we will say the bottommost surface of this whole cylinder. Let's say this is a cylindrical surface. The bottom surface of the cylinder has a surface area S. Same surface area S is at the top of the surface. So this cylinder, if I just redraw it, is acted upon by multiple forces. A force at the top, a force at the bottom, force at the sides as well. That is on the curved part of the cylinder. And the weight force. That is the gravitational force. So gravitational force is the first thing which we want to evaluate because it's the thing which we know is equal to mg. Mg, we know what is mass of the whole cylinder. Mass of the whole cylinder is simply density of the cylinder, density of the fluid into the cross-section area S of the cylinder into the height of the cylinder. So here is what the factor H comes into play. We know that the deeper we go inside a fluid, it's going to contribute positively to the pressure. More the depth, higher the pressure is. That's how different things are designed um, in the world around us, like a submarine. Let's say if a submarine has to go at a very low depth or very high depth, then what can we say? It has to be designed to withstand more pressure. Then we say S into H. So what is the cross section area into the H depth? Cross section area into H depth, S into H, this represents the total volume of the cylinder. So this is the total volume and volume into density. What is that? So volume into density is mass of the whole particular fluid, right? So that is the point. We are not doing something too different. Basically, we are calculating some kind of pressure at this point P, uh, which is going to balance the weight of this whole fluid and the pressure exerted by the atmosphere. Both of the things, that is the pressure and this weight, is going to be balanced by this pressure P. So this pressure T is the one which is basically acting under bottom surface. That is the particles beneath this surface or beneath this whole selected volume, they are exerting a force in vertical direction on the selected container. So because of which it is balanced. That is its weight is balanced. So this pressure T, that is what we want to find. So, if I were to say ki, what is the value of the force exerted by this pressure P? So, this pressure P into the area S, that would be the force exerted by the pressure at this point. And since we know that the pressure at all the points in a horizontal line is same, so simply multiplying pressure with the surface area gives us the force. So this is pressure into area. This is the vertical force acting on the cylinder in vertically upward direction. The weight which we have calculated the mass, multiplying mass with action with gravity. This gives us the weight of the cylinder. And then after calculating this vertical force and this vertically downward force, we are left with the atmospheric force. What is the force exerted by atmosphere? So that force is simply P naught into S. So just like the force exerted by the fluid particles at the bottom of the cylinder, there's a force exerted by atmospheric particles as well. Because of which we had to learn a lot of things that what is one atmosphere, what is centimeter of mercury. So P naught S, that it is acting in vertically downward direction. So we know that all the vertically downward forces, that is P naught S plus the weight. So I'm going to write weight directly. Rho S H into G is going to balance the uh, vertical force. So as you can see, S is common in all the terms on this equation. So it simply cancels out. So the equation which we are left with is P naught plus rho GH is equal to the absolute pressure at a depth H inside a fluid. So this is for a fluids which are basically not accelerated. If a fluid is not accelerated, it will have this pressure. So this is the equation which we are looking for. So next, basically we are looking for the pressure inside a U-tube. So how do we find the pressure inside a U-tube? Pressure inside a U-tube we basically find by saying there is some kind of fluid poured inside particular tube that is joined with another tube in a U shape. pattern. So this is like a single tube and this is U shape. That's why it's called a U tube. So basically we pour some kind of fluid, let's say some fluid of some high density and then some fluid, one more fluid of some lower density at this point. So it shows, it basically for, it develops in this kind of situation, or we say in this state. That is one fluid which was poured like this. It basically is existing at this point, and the other fluid which we poured in this particular uh, tube, it basically is existing like this. So these are two immiscible fluids. Then we say that the density of this fluid is some rho 1 and density of this fluid is some rho 2. So we'll say that if this is rho 1, this is rho 2, what is the net height of one of the fluids? Let's say this fluid is is poured up till a height h. By that we mean is that this length of the fluid is poured in this particular section. So what would be the height of the other fluid, that is rho 2, over some common line? What would that be? So let's say this height is capital H. Uh, So this height is capital H, this height is small h. If one of the factors is known, how would we find the other factor that we have to evaluate? Okay. So it's pretty easy to find actually. What we'll do is that if I have this fluid H, I can find the pressure at this point, point number 1. Let's say this point is 1, or let's say some point A, right? Because A, one word, we have ascribed it to the fluid number 1. This point is A, this is point A, and this is point B. So we take a page out of the Pascal's law that pressure inside a horizontal line in the same fluid is same. So when we draw a horizontal line this point A, that is this point, and this point B, they basically lie in the same fluid, that is fluid number 2. So pressure at B and pressure at A would be same. So we'll say the equation which we can establish is PA is equal to PB. And because A we have chosen for a special reason. The reason being that it not only experiences the pressure because of fluid number 2, it also tells us the information about pressure number fluid number 1. So because of that, we can establish a relation between first fluid and the second fluid. So that's basically a simple logic which we have. We always have to have a point where we can have pressures due to both the fluids. That is a common point. So there, the pressure of fluid number 1 and fluid number 2, they basically balance out. This is a very good thing. So in all these kinds of questions, that is the only thing which we naturally do. We take a point where there is a common point and we draw a horizontal line. And then we figure out what are the different heights. Obviously, there will be different fluids, although there will be different densities. So equation wise, it is pretty easy to evaluate. We can say pressure at A due to fluid number 1 would be atmospheric pressure plus rho 1 GH, right? No matter what container of the fluid is, whether it's a very broad container or very narrow container, like this tube, the pressure always remains the same. It's just like saying that whether you go down in an ocean or go down in a lake, it does not matter what big area which we have. It will definitely have more weight on the whole ocean, on the ocean floor, or in that particular area which we are selecting. The pressure is just decided by the depth value, that is H. So because we are going beneath or going down in the fluid number 1, our pressure is rho 1 GH. That is the only thing which we have to care for. That is what is the density, rho 1. Then this will be equal to pressure due to fluid number 2. So pressure due to fluid number 2 would be simply again atmospheric pressure, that is P naught. So here I have written PA, that is P naught only. So P naught plus rho 2 G into capital H. So these are individual pressures at point A and point B. But since they are lying in the same fluid, that is fluid number 2, we can equate them. So this is a special thing which we can do. So as we equate them, it is pretty clear that P naught gets cancelled out and we get the relation. That is, if we want to find height H, H is simply equal to rho 1 H upon rho 2. So let's do a question on the basis of this. So the question is that we have a fluid, uh, let's say that fluid is the ink of this pen marker, okay, whose density I was not aware of. So when I filled my pen marker ink inside this pen, and when I started writing it, because of lower density or whatever, because I filled it little bit more, it has spread all over the room. So let's say we have a pen marker ink, its density is 0.6 times the density of water. Okay, so 0.6 times the density of water means that its density would be some 600 gram per centimeter cube or 600 kg per meter cube, right? Because density of water is 10 to the power 3 kg per meter cube. Now the situation is that I have the same YouTube like this, right? Okay, so this is how the second fluid is filled in this YouTube. This is the fluid number, let's say the ink of the pen, that is the rho I, ink fluid, that is fluid filled like this, and water is filled like this. Obviously, water and ink actually are miscible fluids, right? If you mix water with ink, they are likely going to get mixed. But we're assuming here, that is the assumption which we have to take, that they are immiscible. And that is the important point. We cannot take this equation or this whole situation in case of miscible fluids, because when the fluid are mixed, we do not know which density which we have to take at a particular point. In fact, when they will get mixed, basically all the fluid will be combined with the second fluid, and they will basically form an equilibrium situation where the height in both the lengths is going to be same, right? So considering our assumption that fluid, ink and water do not mix, we have created a situation where the height of one of the fluids is actually slightly more than that of water. So this particular height, that is the height of the ink fluid above that of water. This height is represented by some small h. Okay, we know that this fluid, other fluid is water, which is filling this whole YouTube. So this is raw water. So question is, if I know till what height I have, or if I know this height difference small h, and I know the height to which I have filled this fluid, ink fluid HI, if I know this HI particular height, or let's say if I know small h, this particular height if I know, can I find HI? Right. So I think we can. Let's try to form an equation. So we'll again say that, okay, let's draw same common line like we did in the previous idea, that there is a common line like this. This is point A, right, which is at the intersection of the two fluids, and this is point B. So pressure at A and pressure at B, they are going to be equal only. So we will say that the pressure at A is simply rho I G H I plus atmospheric pressure, which is P naught, And similarly, pressure at point B is going to be P naught plus density of water G into this complete height, right? So if you see this particular length that we have taken, this complete length is HI. So what is this smaller length going to be, which is putting the pressure at point B? Only there we have to be careful, right? So basically this particular height, that is smaller height, it is simply HI minus the height difference between the columns in the two U-tube sections. So we will say this is HI minus the height difference small h. The height difference small h, it is given to us as some 5 centimeter. So let's plug in the values again. Atmospheric pressure again gets cancelled out, so it is not able to put any effect to our equation. But density of the ink is 0.6 times that of water. We can directly write it like this. This is 0.6 times density of water. G HI we have to find is equal to density of water G into HI minus H. So we can simply say 0.6 into density of water G HI is equal to density of water G, putting the value of small h, that is 5 centimeter. So here we don't have to change 5 centimeter into meters because all the units are getting cancelled out. Basically that's the thing which we have to do. That's why I've written this whole equation again only, because I want to explain about units. Units basically helps us in identifying or cutting down our time. Let's say if density of water here and density of water here have had different units, then I'll have to put that whole thing here, right? So that would have taken more time. So that's why we basically express the density of the other fluid in terms of density of water, because it is getting cancelled out. If it were not getting cancelled out, then we would have to put that value. I would have done more calculations. But that's not the point. We basically try to express the density of the thing which we don't know in terms of thing which we know. So it basically cancels out. G also will get cancelled out since both the sections of fluid are on the same planet. And HI, that is what we have to find. So this is simply 0.6 times HI equal HI minus 5. Again, HI and this whole thing, they will have the same unit. So even if we have converted 5 centimeter into meters, HI will also follow the same thing by its own. So we won't have to take take an idea to think that whether what HI unit is going to be or how will I think about the unit of HI. Because in the same equation, we are going to follow the same units. If this term is having a unit centimeter, then automatically HI will also follow the same unit, right? So that's why we can simply say that the unit of the value small h, we have simply put it like this, 5 centimeter. And HI is also going to come in that unit. The thing which you have to remember is that in exam, if the question is asked express HI in terms of meter, then you have to be careful. Okay, after getting the answer, don't jump. Basically say that you have to convert HI into meters, right? This implies 5 is equal to 0.4 times HI. So this value is going to be some 12.5 centimeter value. So thank you for joining.